these two functions are equal to each other. But I said that I can prove it without using the generation function, so just by definition. So if I have the partition of n into odd parts, I can manipulate it and move it and have to get the one-to-one correspondence into the pairwise distinct summons. So here I can just write some example. For example, if I take 7, I can so pairwise distinct summons, it will be just 7, 6 plus 1, 5 plus 2, 4 plus 3, and then like 4 plus 1, 4 plus 2 plus 1. I think that that is all that I can do. And here, if I want to look at the odd summons, I can write like all ones, or 4 ones and 3, or 2 ones and 5, or 7, or 3 plus 3 plus 1. So I have here 5 and here 5, and I want to produce the map from the first set to the other set to be this map like one-to-one correspondence. And all I want to do, and here I want to use. So if I have pairwise distinct summons, I want to construct from it, for example, from here to here. So I want to construct from pairwise distinct summons. I want to construct some partitions into odd summons and inverse map to this one. And I use what is simpler to calculate. Oh, I think I will have from the left to the right. So for example, I have some partitions of n into the odd summons and so on. If I combined all the equal summons into one group, then I will have like L1 ones or L3 threes and so on. So after that, all I want to do is just to express all this, find the expression of these numbers L1 and L3, L5, and so on, such that I will obtain the pairwise distinct parts. And I will use know how to sort is spelled in English. So I just want to express every number as the sum of the powers of 2. So I write that this is easily, you can easily prove that each natural number can be expressed as sum of some powers of 2. So for example, if I take like 7 ones, I can write this 7 as 1, and 7 is 2 squared plus 2 plus 1. So I write this as 2 squared plus 2 plus 1 times 1, and I will obtain the partition of n into pairwise distinct numbers. For example, if I take 1 plus 1 plus 1 plus 1 plus 3, then I will have 4 ones and just 3, and so it will be just 4 plus 3. If I'll have 1 plus 1 plus 5, it's just 2 times 1 plus 5, so it just will be 2 and 5, and 3 plus 3 plus 1 is 1 plus 2 times 3, it will happen 1 plus 6, and 7 goes to the 7. Why when I'm doing this, this will be pairwise distinct numbers? Because every number is just easy lemma. So every natural number has unique expression every natural number n has unique expression like 2 to the power s times L, where L is odd. So for each number n, I have a unique decomposition where I just put all the maximal power of 2 where I can get from this number, and then I will have the left number will be odd. So I can, so if I want go to the opposite way. So for example, I have n, and I just write the different n1, n2, and k is distinct numbers, distinct parts. I just write each of these numbers as 2 power something times L something, where L1 is odd. And then I will just write this as sum of these odd parts times the so I will repeat these parts such number so that the sum will be equal to ni. And so from here I will obtain like L1 plus L1 times 2 to the power S1 plus etc. plus Li plus Li times 2 to the Si, and so on. And so from the pairwise distinct parts, I will obtain some of the odd parts. And I can do inverse image because, so inverse map will be the following. I take the odd parts, combine them, and then I will, so like here, I will write each coefficient here as the sum of the power of two, and then I will separate them, and I will obtain the different the pairwise distinct numbers, because from each number there will be either different power of 2 or different odd number here. So they all parts will be pairwise distinct. Is it clear, or maybe you have some questions? So I can maybe repeat this once more. So if I have, so I can have, I want to give you two maps from the pairwise distinct partitions to the odd partitions, and from the odd partitions to the pairwise distinct partitions. So if I have, pairwise distinct partitions parts, then I can just each part I will write as 2 to some power times odd, and then I will change it to the just sum of these odd parts, like to the power s times, and I will have decomposition where all parts are odd. And if I want to start with the odd parts, I will combine them, all the odd parts, into some number m. Then I will express this number m as power of 2, and then I will have here sums like 2 power u 2 power n1 times L plus 2 power n2 times L, and so on. And so here we'll have all these parts will be pairwise distinct. And you can easily prove that this maps is inverse to each other. So this will be one-to-one correspondence. So it's a little bit hard to see, but you can prove it without using the generation functions. Maybe proof using the generation functions it will be simpler than this, or maybe this will simpler. I don't know. Do you have any questions?
No, sir.
Okay. Full did understand, or you maybe need more examples, or is it okay? Is it right?
Yeah, I think it's okay.
Okay. So we've finished our combinatorics part. So maybe if we have much time at the end, I think we can return, because Follow asked me to talk about cyclic permutations and maybe recurrence relations where you have maybe more complex recurrence relation where we have nonlinear recurrence relations. So maybe I will just give a lecture maybe in the middle of December. But now I think we can go to the graphs and graphs part of the course. And so if it will be okay, so maybe we'll have additional lecture on combinatorics. So I think you are all familiar with the main notions of the graphs, like vertices, edges, cycles, and so on. I can
Sir, I have a question.
yeah.
Yeah, we have an exam next week, right?
Midterm, yeah.
Yeah, midterm. So, what's the syllabus for the exam? Like, is it whatever you covered until now, or
Yeah, what we covered it now. So we have like 6 weeks, and
yeah?
so there will be 6 tasks. 6 tasks is each task for one task for 1 week.
Oh, okay,
Yeah.
okay.
Okay.
Yeah.
So usually graphs is just the set of the vertices and set of edges. So set of edges is just the pair of vertices, and there is some distinct definition. So you can have graph, have oriented graph, or graph, have multigraph if you can take the two or more edges between the same vertices and so on. But let's now we'll start with the simple graph, so we have no orientation, and between two vertices we either has one edge or no edges at all. And first I want to talk to you about planar graphs. Do you cover it? I don't think that you cover it in the first part of the course, but I need to ask you: do you hear of it anywhere about the planar graphs?
No, sir.
Okay. So what is it? We can usually when you think of the graph, you don't think of it about the just set of vertices and set of edges. You just think about some picture of it, and we can try to illustrate our graph as picture right on the plane. So we can call that graph. So we can just try to write the vertices as points on the plane, and then we can illustrate edges as just the lines or curves that between these vertices. So we just can try to look at the image of this graph on the plane. So if we can draw a picture where vertices are the points and set of edges are just the curves between connecting these vertices, and if we can write this picture where no edges are crossing outside vertices, then we can call this graph is planar. Is graph that can be embedded on the plane. We can correspond vertices to the dots of points on plane, and edges are just curves connecting corresponding points such that edges are not intersecting with each other outside the vertices. So, for example, here is a picture of planar graph, and so we can call the embedded graph or the plane graph is just this picture of graph on the plane. So the image is called the plane graph or the embedded graph. So the main question is how can we determine? So we can take the arbitrary graph. We have set of vertices, set of edges. Can we or can we not embed it on the plane? So for example, if I have like simple graph, for example, the K3, or for example any tree. So of course we can, if we have tree, we can embed it in on the plane. But what about more complex graphs? So for example, K3 we can write this on the planes. What about K4? Okay, K4 is so this is not a plane graph. But is it K4 is planar graph or not? Can we images on the follow?
I don't. It's not a planar graph since the edges intersect, sir.
Yeah, but maybe we can write another picture where edges does not intersect to each other. Can we write another picture? So can we? So here.
Yes, sir. If we take the edges outside instead of
For example, we can write this edge outside the square, and so
yes, sir.
So this is not a plane graph, but we can illustrate this graph like in this picture, and so it will be the so here I can give a picture of this graph on the plane such that all the edges are not intersect each other. So K4 is planar graph. What about K5? K5 is more complex graph. Okay, here, if I just write this as pentagon, I will have too many intersections, and I can try to just write some of these edges outside. So here I can like this one and maybe this one and maybe this one. But here I will have a problem that I can. So I don't know what to do with this last edge because I cannot draw it such that it not intersect with other edges. And the problem is my picture wrong? Maybe I will try to find a picture when this graph, a picture of plane graph of K5, or cannot. So or maybe I cannot do that. And this is the main question: how can I determine by the definition of the graph if it is, if I can illustrate, embed it into the plane, or illustrate it on the plane, or I cannot do it. So the main question is, okay, so first we start with the we'll start with the plane graph and try to find some connection between the number of vertices and number of edges and some so do we have like some identity between them or some inequality that restricted us to the planar graph. So okay, we understand that we cannot have much edges. So if we have like 10 vertices and 20 edges, so maybe we cannot embed them into the plane because there are too many edges. And so I can have some restrictions. And first I assume that, so if I take the graph G, I will first assume the graph G is connected. Because if I have, so I can divide my G into the connect parts and look at them, each of these parts, because if each of these parts is embedded on the plane, that I can write the whole picture, I can just embed the whole graph into the plane. So I can assume that my graph G is connected. And then if I have, if it is planar, then I can look at this picture that so I can look at this plane graph. So I can look at this picture where I'll have my graph embedded on the plane. And if I look, I can see that I have what I have. I have vertices here. I have edges here. And also my whole plane are divided into connected parts. So here I will have like so what is this connect parts? It's called faces. And it is just linear wise connection parts. So if I can, so the one of this part is just the number of the points that I can connect without crossing the edges of my graph. So for example, here I can connect two of these points without intersections with the edges. So these 2 points belongs to the same face. Okay, so if I can define what is the face, then I have the number of vertices, the number of edges, and the number of faces. And I want to prove the famous formula called Euler formula. So if G is connected and planar, then v minus e plus f is always equal to 2. So for example, here I can just calculate. So how many vertices do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Edges will be 18, and faces I can find here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 10. So if I calculate it like 10 minus 18 plus 10 is equal to 2. For example, for this graph, it is correct. So maybe I have a hope that it will be correct for any planar connected graph.
Sir?
Yeah.
So the whole graph is one face.
Yeah. For example,
Okay.
Okay. So if you have, for example, a tree, then you have only one face. And you know that if this graph is trees, and you have vertices will be one more than edges. The number of vertices is so.
Yes.
If you have v vertices, then we have v minus 1 edges. So it just will be v minus 1 plus 1 is equal to 2, and so it is obvious. So it is just the start of. So it is true. So we can prove this many different ways, and prove it by induction. And we can go on induction by edges or vertices. But I think it is better. So if we start for the arbitrary planar connected graph, then we can try prove it by induction by edges. Prove by induction on the number of edges. So we fix the number of vertices. So we trust vertices is v, and then we can put by induction by the number of edges. And so the minimal number of edges will be v minus 1 if graph is connected, and this will be 3. And for 3, I can prove it just by so I just prove it for just proving this formula. Okay. And so all I need to do just add some edges on this picture. So I can just connect like 2 of these vertices, 2 of these vertices, and so on. And by each new connection, one of the faces will be divided by will be divided into 2 parts. So each edge, so if I draw a new edge, then some of these parts, some of this face, some of face where it will be edge where edge is belong to, will be divided into 2 now new disconnected parts. So for example, if I draw this edge, then I will have this new face, and if I draw this edge, I will have this new face, and so on. If edges is equal vertices minus 1, then G is 3 and has only one face, and v minus 1 plus 1 is equal to 2. And if edges is greater than vertices minus 1, then I have a cycle in G. So I choose an edge in the cycle, and just forget about it. So if I denote, so this will be edge called A, for example. If I denote by G the new G tiled, the new graph where I just forget about this edge, then I will have by induction hypothesis the number of vertices minus the number of edges plus the number of faces is equal to 2. And then when I draw this edge, I will have one new face because face it. So now for the graph G, the number of faces is equal to number of faces plus 1, because if A belongs to face alpha, then alpha is divided from the F tiled, then alpha is divided into 2 parts. And so by induction, I can prove this formula holds for my graph. And so for each planar connected graph, I will have the number of vertices minus the number of edges plus the number of faces equal to 2. Do you have any questions?
Yes, sir. I didn't really understand this one. I understood the one for the tree, but
Okay, so for the so if you have planar connected graph, you just so if you have trees, and you can prove it by calculation, and so if you have the arbitrary planar connected graph, you just find the cycle. So for example, here I can find the cycle, and then I just choose arbitrary edge. So this will be just the edge A, and then I forget about it. I can draw it out. So if I draw it out, I will have a graph with a lesser number of edges, and by induction hypothesis, I can prove it for this graph that this formula holds. So for the new graph without this edge, I can prove that the number of vertices minus the number of, I will have like this formula. But for the different numbers of edges and faces, because the vertices are the same, the number of vertices is the same, but I change the number of edges and number of faces. How I change it? I forget about one edge, so new number of edges is just number of edges minus 1. And also when I forget about this edge, so these two different faces became 1.
yes.
And so my new number of faces is just faces minus 1. And so when I
F minus 1.
yeah, F minus 1, because new graph will contains one lesser face, because 2 faces became 1. And so if I just put this into this equation, I will have F V minus E minus 1 plus F minus 1 is equal to V minus E plus F is equal to 2. And so I prove the formula for the new edge. So I prove it by induction. So if the edges are so the edges is like equal to the v minus 1, then I prove it, and then I prove to the edges when the edges is equal to v, equal to v plus 1, and so on.
Yes, sir.
Okay.
Yes, sir.
Okay. Do I need to give another example, or I can continue?
No, it's okay, sir.
Okay. So if you what if you have so from this from the Euler formula we can obtain some properties, some inequalities of the number of edges and number of vertices. But if I want to, write the inequality of something like that, if for connected planar graph something like v is not, no, I think like e is not equal to 3v minus 6 holds. But how can I do it? I can prove the inequality between edges and faces, and using the Euler formula, I can obtain the inequality between edges and vertices. So I have lemma for planar graph. I can write like 2e is not greater than 3f. Why is it so? Suppose we have a planar graph. So maybe inequality into the so I just prove it and then I find what is greater than. Yeah, I think maybe is it way. So suppose we have some planar graph, and then we want to calculate the number of edges and the number of faces. So we know that each face contains three or more edges inside and on the border. So we maybe need to assume that here for planar graph with at least I don't know 3 edges. So because we need to, each face contains more than 3 edges. So if we choose each face, then it will be, if you look at the border contains at least 3 edges, or maybe more. And each of the edges are containing in 1 or 2 faces. So it will be, we can also write some additional edges into the faces, but usually the edges will be just on the border of 2 faces. So if I write 2e, it will be exactly the number of edges into at least this number of edges into one face. So we can just separate this. So we can write this each edge we can count twice, and it will be the number of edges corresponding to face. So if I just calculate the number, so if I double the number of edges, then I will calculate the number of, it will be more than the number of edges on the border of each face. And each face contains 3 edges or more. So I can write like this inequality. So this is more than the edges on the sum of number of edges on the border of faces. And so each face have 3 or more edges on the border, so it will just like greater than 3 times f. Do you understand? Do you have any questions? Maybe I need to write some more examples. So if I just take the edge and write this 2 times, one on the side and one on the outside, one on the outside, then I will can summarize it, and I will calculate the number of edges inside each face. And the number of edges inside each face is 3. And so I will have this inequality. Okay?
Okay, sir.
Okay. So if I do that, I can so I proved that 2e is equal or greater than 3f. And if I use this formula, so for connected graphs, I can just take that f is equal to 2 plus e minus v. And so here we'll have 2e is greater than 3 times 2 plus e minus v. It is equal to 6 plus 3e minus v. And so I can write this that minus 3v. So 3v minus 6 is greater than 2e. So it is a, oh no, not 2, but just 1. Yeah. So here I have 3e minus 2e just equal to e. So it was lemma 1. So lemma 2 will be just that for connected planar graphs, here is not greater than 3v minus 6. And so here's the proof. I can just write it. So we have by lemma 1 and f is equal to 2 plus e minus v. So if I just do the calculations, I can obtain that e is less than 3v minus 6. Okay, let's use it for the chi5 graph. Okay, so how many edges do you have chi5 graph? And how many number of vertices do we have? It's just the full graph on 5 vertices. So we have every edge connecting. So I assume that you all understand that the number of edges is equal to 5. A number of vertices is equal to 5. And what's the number of edges?
10.
10, yeah, okay. So if we use this inequality, then we will have that 10 must be not greater than 3 times 5 minus 6, which is equal to 9, and our inequality is broken. So if chi5 is planar, then we'll have the contradiction. Okay?
Sir, so for any connected graph that the inequality does not hold, that means that graph is not a planar graph.
Yeah.
Okay.
Because we just proved that if graph is planar, then this inequality holds. So if inequality is broken, then we cannot embed it into the plane. Okay.
Okay, sure.
Of course, if you have like T6, T7, and so on, or every graph that connected that have chi5 as subgraph will be not a planar, because if we cannot write a K5, then we can't write every graph that contained it. So is not a planar graph. Another example of the not planar graph is K33 bipartite graph with 3 vertices into each of the parts. I can write an image here, so just
Sir, so number of vertices is 6 and number of edges is 9.
yeah. So, but here, if you write this inequality, like E equal to 3 by 6 minus 9, then minus 6, this would be not a contradiction, because 9 is less than 12. So we need to use more strongly inequality, or maybe some other inequality that holds for this graph.
Sir, so the inequality we hold before, it doesn't hold for bipartite graphs.
Why?
I'm asking, sir.
Yeah. So if the inequality holds, it doesn't mean that the graph is planar, because we just prove it. So we just prove that if is planar connected, then this inequality holds. But we didn't prove it to the other way. So maybe we have some graphs that this inequality holds, but it's not planar.
Oh, okay.
And so okay, I will have you a hint, and I will give you like 5 minutes. Maybe we can take a little break, and afterwards I will prove it for the K33. But here we can think that if we look at this graph has some different structure, because each phase, each cycle of this graph, and hence each phase of the. So if this graph is planar, then each phase will contain will be bordered by the number of edges in the cycles. So each cycle of this graph, how many edges can have the cycle of this graph? So can we obtain the cycle with 3 edges here?
No, sir.
Okay, so
I think the only cycles we can have is squares.
yeah, we can have cycles like they must contain even number of edges. So we can have 4, 6, 4 or 6 edges. So I think we can use it as a hint to prove more strictly inequalities than we have, and this inequality will not hold for this graph, and so we can prove that it's not planar. But I think we can have a little break, like 5 or maybe 7 minutes, and then we'll continue. Okay?
Okay, sir.
Okay. Okay, I think we can continue. So maybe someone has a solution? No? An idea? Or how can we improve our inequality to maybe obtain some more strict inequality on the edges and vertices? No?
No, sir.
Okay, so what if each cycle has greater than 4 edges? Then remember when I prove the inequality that 2e is equal or greater than 3f, what I do is just I look at each face and try to calculate the number of edges on its border. So if each face contains more than 4 edges, then I can write this inequality as 2e equal or greater than 4f. Is not less than 4f, because I can do the same idea. Each face contains 4 or greater edges, and so if I multiplicate edges by 2, I can it will be more than all the edges in each of the face, and so I can have more strict inequality. So do you understand? Or maybe I need to be more clear.
So can you explain? So you said that this one is a stricter inequality?
Yeah, because I prove that 2e not greater than 3f, but greater than 4f. So I need edges not as the 1.5 of f, but I need edges is greater than 2f. So I need more edges to this graph to be planar.
So if it is 5, then what will happen?
If what is 5?
If each face contains more than
if each
5 edges.
If each face contains more than 5 edges, then we will have 2e greater or equal than 5f. For the same reason, because I can calculate all the edges into the face. So 5f is the least number of the edges in the border of this face of the faces. So I look at all of the faces and collect how many edges on the border do they have, and they will be at least 5f. But each edge I will calculate 1 or 2 times, so it will be less than 2e.
Sir, please, can you do it with this diagram that you drew on the left? So this diagram has 4 faces.
So maybe I can write like bigger diagram and more complex diagram so you can see it. So I have a big planar graph, and each face contains more than, for example, 4 edges. So if I look at these edges on the border, there will be at least 5 of them.
So what do you mean by a border?
Border of the face is just the so if some edges is contained into the border, it means that for example here I will have this edge, and it will be it belongs into it lies in the border. So the edge is on the border. If I cross this edge, I will move to another face. So for example, this this edge is border edge because it dissects two different faces.
Okay, so the edge is in between two faces.
Yeah, edges in between two faces. Yes. So border is just the edge that belongs to the two faces. So border edges is edges that contains into two faces. Okay.
Okay, so how many so I think it would be easier with this small diagram you drew over here. The small
Okay.
diagram on the top
Okay.
left.
Okay. So I have four faces. One
Yes, sir.
one big face and three small. And so one the first one has this one has five edges. This one five edges. This has five edges, and the um, out one is have 1, 2, 3, 4, 5, 6, 7, 8, 9, like 10 edges. Maybe 9. No, 10 edges. So I have four faces containing 5, 5, 5, and 10 edges. And so if I double the number of edges, it will be just the sum of these numbers. It's just 10 plus 5 plus 5 plus 5. If I, so maybe my mistake here somewhere. So
Sir, does one of the edges have six? One of the faces have
yeah,
six edges?
yeah, 6 yeah. So it will be just it'll be just the number of edges or 2e. So I can write this 2e is greater than 5 times the number of the faces because each face contains 5 or greater.
Oh, okay. Yes, sir. Yes, sir.
So if I have this uh, so if I know that each face contains more than 4 edges or more than 5 edges, then I can write the corresponding inequality. Okay.
Okay, sir.
Here, when I have the graph k,
So,
yeah,
sir, but why do we write to E? Why does the sum equals to E? Why doesn't the sum just equals E?
was the sum equals to 2 times e? Yeah, you ask.
Yes, sir.
Because I so each edge I just calculate exactly 2 times because it belongs to the two faces.
Oh, okay.
So
So each of the edge belongs to the big face and also the small face?
yeah,
Oh,
some of them is
and the borders also.
yeah, yeah.
Oh, okay.
So each edge is just the border of two faces. But and additionally, maybe I have some edges into the faces, but it doesn't matter because if I double the number of edges, it will be just a great number. So we just this inequality holds for these pictures, and I can add any other edges, and this inequality will be just stronger. Okay. So I can forget about these edges because I calculate, so I can uh, calculate them only one time and it will be okay. So if I double them, it doesn't matter. So I can prove this inequality only on the border edges, only of these edges that are border of the some faces. But so I can just add some borders, some edges inside faces. Okay. So it okay. So therefore, therefore, for this graph, all faces contains none less than 4 edges. Then we can write more strict inequality. 2e is equal or greater than 4f. And then if we use the Euler formula, then we will obtain that e is greater than 2 of 2. So f is equal to 2 minus v plus e. And so I can write it here. It will be equal to 4 minus 2v plus 2e. And 2v is greater than 4 minus plus e. So e is less than 2v minus 4. And so for our graph, we'll have, as I said, e equal to 9 and v equal to 6. And e will be equal to 9 and v will be to 6. To 6 minus 4 is just 8. And again, we have contradiction. That to the proposition that K33 is planar. So K33 is not a planar graph. Okay?
Yes, sir, it's clear.
So we proved that Chi5 is not planar. And we proved that K33 is not a planar graph either.
Sir, so
Yeah.
the algorithm is to find the minimum number of edges to make a cycle in the graph. Then we can substitute it into this inequality to figure out whether it's a planar graph or not.
Yeah, but something like that. But now I will formulate the theorem of characterization of graph if it is planar or not. So,
Okay.
so we prove that K5 is not a planar, K33 is not a planar, and what can we already obtain? So if our graph is containing K5 or K33, then of course it's not a planar because we cannot. If we can embed it on the plane, then we can embed it a subgraph like K5 or K33. So if G is contains K5 or K33 is as a subgraph, then G is not a planar graph. But also we can just do, so we can put the additional vertices onto the edges and do some like this. So for example, if we take K55 and then we just take the edge and add some new vertices here in the middle of the edge, then this graph is also not a planar graph because we can forget. So we can make this edge as one, these two edges as one. We can glue them together and obtain the K5, and K5 is not a planar. And so we have the theorem. So we can look at this as a so-called homomorphic change of the graph, and so we can give the definition.
Sir,
Yeah. Do you know what is a homeomorphic graph means now?
No, sir.
So homeomorph, if we can obtain G1 from G2 by these operations. So first of all, we can so if so we can take the edge. If we take the we can take the edge and take, so put the point in the middle of the edge and make two edges from this one. So one edge, we can I can maybe draw a picture here. So this one edge we can write this as one new vertices and two new edges exactly from this one. So if you have like A, B here, so it will be A, B, and C here. So we can do this operation from AB to ACB or from ACB to AB. Okay? And also we can, what we can do is this, let me check it.
Sir, so we can form an edge AB by joining two edges AC and CB.
One moment. I want to check. Okay, so if you have two vertices and the edge between them, then you can add one more vertices between them, the vertex C, and then you can connect it to the A and B. So you instead of one edge, you get two edges from instead of one edges AB, you will have new point C and two edges AC and AB. Okay.
Okay, sir. And sir, so K5 and K33 are the minimum graphs that are not planar.
Yeah.
So is there a proof for that?
Yeah. So maybe I just need to. So if I take this into so if I use the separation, I can change a graph a little bit. So I can just forget the new vertices. Maybe I can lose some vertices. Maybe I can add some vertices. But now I have the theorem that G is a planar graph. If and only if it doesn't contain a subgraph. It doesn't homomorphic to a graph containing K5 or K33. So G is not homeomorphic. So maybe I can write this like G has no subgraph, homeomorphic to the K5 or K33. I think it's named after the Kuratovsky. Kuratovsky. So we proved it from the from left to the right. It is simply because if G has subgraph isomorphic homeomorphic to the K5 or K33, then of course it's not a planar because we can take just this subgraph and then take a homeomorphism which is of course doesn't do anything to the planar, because if we just add the point in the middle of the edge, just forget about the point in the middle of the edge, then if the first graph was, if G1 is planar and G1 is going to G2, then of course G2 is also planar graph. So if
I'm so sorry, I didn't get that. From
yeah.
left to right.
So if G1 is going morphic to G2, then if G1 is planar, then G2 is planar. Why is that? Because if you can write something on the plane, we can embed something on the plane. Then, of course, if you just put the new vertices in between of two existing vertices already, then it already also be planar subgraph. And if you have like some
Yes, sir.
some edge here and just if you have two edges and forget about this point that in the middle, then of course the new graph also be planar. And from this, you can easily prove from left to right. So if G is planar graph, then of course G cannot contain any subgraph isomorphic homeomorphic to K5 or K33. But the other part of the proof from right to left is not so easily. So I think we can left it without the proof. I think it's okay because it will just technical proof, and I will spend like an hour to prove it, and I don't think it is necessary. It's technical. Okay, so maybe you have some more questions? No? I think we will have some more talk about the planar graph in the beginning of the next lecture, but the next Wednesday will be midterm, and I think the Wednesday after that it will be the 4th of November, and I think we'll have no lecture on this day because we will have some celebration of in Russia it is celebration day of some something like, I don't know how to call it in English. So we can have any lectures on this day, I think.
On November 4th?
Yes.
So it's Unity Day.
Yes, it's Unity Day. Yeah, I will find how to call it in English because I don't have no idea how to call it in English. But yeah, it's Unity Day, and so we have no lecture on this day.
Yes, sir. I still don't understand how the proof that K5 or K33 is the minimum subgraph we can have that would not make a planar
I
graph.
told you that the other part is just technical, and I will not. So it is not
okay.
very easily to see, but you can prove it, but it's not. So it is true that every graph that is not planar, it must contain either K5 or K33, or homeomorphic to the graph that contains the graph homeomorphic to K5 or K33. But it's not easily to see. It's not easy. It's not.
Okay.
You just need to look at some cases.
Accept it.
Yeah. Okay. I think that's all.
Okay.
So if you have any questions, you can ask me in Telegram, I suppose. Yeah.
Okay.
So, okay. So that's all for today. Thank you. If you have any questions.
Goodbye, sir.
Yeah. Bye. So.